uh, lecture 15. So this is the end of our front end of line emulation, and we will switch to another topic in this lecture. Let's go to lecture 15. So up to now we have fabricate source and drain application, and once we make this epi, then on top of this source drain epi we also make cell side. So introduce certain metal, and that is silicided. Silicided means that initially that was metal like nickel, but we have something corresponding to nickel silicide and nickel silicide. It provides good buffer layer between eventually the metal and this silicon or silicon germanium case. By the way, at the end of our previous lecture, after the lecture is over, then one student came to me and asked about silicon phosphide, use of this one for doping for N MOSFET. Usually, in many cases, when we use ion implementation for doping, N-type doping, high density N-type doping, so usually we use many cases arsenic. Arsenic is much heavier. So since this is heavy, once it is injected into this silicon channel, then it does not move because that is quite heavy. But in the case of our epitaxial growth for source and drain, the atomic size between silicon and arsenic is larger than the difference between silicon and phosphorus. So that's the reason why if we introduce silicon arsenic one as a growing material of our silicon epitaxy layer, then it introduces severe defects inside this. So this is not a good way to proceed. So that's the reason why instead of we have this for N-type dopant, but in this case we are using silicon phosphorus. And also there has been also another attempt like silicon and slightly doped with carbon. So of course the carbon content is much lower than the compound semiconductor called as silicon carbide. So there is a material called as silicon carbide. This is really regularly placed compound material between silicon and carbon. They are equally populated. However, instead of that, when we say silicon and colon NC, it means that we introduce a small number of carbon inside this silicon. But also that is not that much used. So usually we use phosphorus as a doping material for N-type dopant. So simply speaking, silicon phosphorus is the right description for epitaxial growth. And now let's come back to our original lecture. Now we have done with the source drain formation. Then the remaining part is making gate. Then where can you make a gate? Of course, for the place made by dummy gates. There are dummy gates, and that is just polysilicon. So we will actually remove this polysilicon because polysilicon was just a placeholder taking about 20 nanometer inside this system, so that should be replaced. So we will talk about how can we do this job. But important point is control of work function. This is quite important, and actually I heard that actually there is a rumor about this work function material even inside a certain semiconductor manufacturing company. How can we introduce this split of work function is regarded as one of the top secret, so they do not share the information between engineers. So no, so therefore, what I wanted to say is what is actually being done in there. It is not that easy to say, but from literature we can find some ways. First of all, we have to understand this situation. This is a TSMC presentation, maybe in the last year. I don't remember exactly, but anyway, it is for its N2 technology. Of course, N2 technology is no longer related with FinFET. This is their first generation for nanosheet MOSFET. However, anyway, important one is in their implementation, they provide both for MOSFET and PMOSFET 6 different threshold voltage options for our devices. So you can see that here certain numbers. What are they? I don't know, but this one SVT, here S is for standard. So please have a look at its value. Its value is, in the case of a PMOSFET, about minus 0.3 volt. And when you have a look at its MOSFET value, it is also about 0.25 volt. So what is it? This is related with, there is a lot estimation about threshold voltage. When you have VDD, then nominal way to have the required value or desirable value of our logic technology is just to take 1/3 of this VDD. So this is the typical number. Please think about our VDD. In this case, what is our typical value for VDD? This is now 0.7, and we are now going to down to 0.65 or even 0.6. And please take 1/3 of this number. You will find that this number is around 0.23 volt. So that is regarded as the standard value for threshold voltage. So now think about this one. If we have a certain threshold voltage about 0.23 volt, and if we have another device from the same technology, however, threshold voltage is lowered by, for example, lowered by 0.1 volt, then what will happen? If we apply VDD equal to 0.7 volt to its gate, then you can find that actually gate overdrive voltage, the difference between gate voltage and threshold voltage would be, in this nominal case, it would be 0.47 volt, and now it becomes 0.57 volt. So with lower threshold voltage, then we can enjoy much higher value of gate overdrive voltage. So simply speaking, with this transistor, we can expect a lot more current than the standard one. So where can you find the number corresponding to 0.23? So roughly speaking, these are the one corresponding to 1/3 of them. And if we go to this direction, then we can reduce actually power consumption. So since threshold voltage is increased, it means that we can reduce the off current, the current flows when even when we apply zero gate voltage to the gate. So this is the direction for further reducing the power consumption. And also if we go to this direction, then obviously this is more power consumption. So power from the power consumption view, this is not a good direction, but at the same time we can severely increase the performance because this is just to increase gate overdrive voltage. Please note that in many cases we don't have any further knob to change something in this family. For example, we have 6 different devices with different threshold voltage, but since that is used for standard one, I will make another treatment for this guy. And if we have extremely low threshold voltage, I will do some additional treatment for this one. Usually our technology is so tight, so we have not many other knobs to tweak their performance. Usually what we do is just changing threshold voltage. It means that geometrical factors are the same size of a transistor, and everything seems to be just the same, and only changing this threshold voltage we have to control this performance and trade-off between performance and power consumption. So which one is best? There is no single best device. Usually what we have is trade-off between threshold voltage and power consumption and performance. So we have to select the appropriate device for appropriate conditions. For example, if we are really performance hungry, for example, if we design some core part of our ALU, so arithmetic unit, then we have to provide most powerful devices in our technology for that purpose, that case, because they have to repeatedly perform the mathematical calculation and use the very fast output for our requirement or question. And if we are just to have a relatively relaxed condition, just to on and off slowly, then of course we can use the device with higher threshold voltage. So one I wanted to say is this is the requirement. So we need to supply different threshold voltages to our customers, because our customers are designers, and designers wanted to have different options to select their threshold voltages. Then how can we supply different devices with different threshold voltage? Then the only way is changing threshold voltage. And how can we change threshold voltage? Only our gate stack itself is used as a knob to control threshold voltage. Why I'm saying this one? It was not the case in former times. Decades ago, there was different ways to change threshold voltage. Please remember that our MOSFETs can be just schematically drawn in this way. And here we have a gate and silicon dioxide layer, and here we have a silicon substrate. And threshold voltage is the property of this vertical stack. That is nothing related with this source and drain. And here we have a gate and insulating layer and silicon substrate. And what we have done previously was control the doping profile, doping density in this silicon part, because at that time, former times, we have not much way to control the work function of this gate material. So people thought that, okay, once we have a certain material, gate material, aluminum or something, then work function is just a given number. Then how can we control this threshold voltage? That was this changing the doping density, accept density, or donor density for N MOSFET and P MOSFET. That was the way to control threshold voltage. Simply speaking, if you provide more and more impurities into your silicon substrate, then you can increase threshold voltage. And if you don't have enough number of doping density, then your threshold voltage in terms of its absolute value reduced and goes close to zero. That was the situation. However, historically there was a big problem obtained from this trend. People always reduce this silicon dioxide thickness, so effective oxide thickness was getting shorter and shorter, and now gate was quite powerful, so it can easily turn on our transistor. So the general trend was, since we are shrinking everything, we have to increase also doping density, not reducing, but it should be increased. So in order to keep our threshold voltage in a reasonable value. It means that, let's think about this situation. We had a very successful technology and we have reduced everything, but assume that there is no change in our doping density. Then what we have is significant reduction of threshold voltage, so it cannot be used our proper purpose. So we were enforced to increase threshold. In order to increase threshold voltage, we were enforced to increase doping density, and previously doping level was in the level of 10 to the 18 per cubic centimeter. Please remember that the order of our doping density for source and drain is about 10 to the 20 per cubic centimeter, and we are now trying to go beyond 21 per cubic centimeter. So 10 to the 18, especially having some leading numbers, not 1, 2, but if it goes to 5 or something, then this becomes really comparable, non-negligible, even compared with this high doping density. That was quite much problematic. Why? The reason was quite obvious, because since we have so high density and since we have so small density, that introduces some problems. So size of our channel region becomes ever decreasing, and doping density of our channel region is ever increasing. So what will happen? Now within this small volume, we have to introduce some impurities, and now whether that number increase 1 or 2, that introduce a lot of difference. So let me just give you one example. Let's say that there is one more additional dopant atom, and it is found 10 nanometer by 10 nanometer by 10 nanometer cube. So then what is it? if we have this small cube, 10 nanometer, 10 nanometer, 10 nanometer, and when we have just one additional atom, that is corresponding to the number of 10 to the 18 per cubic centimeter, because this 10 nanometer is corresponding to 10 to the minus 6 centimeter, 10 to the minus 6 centimeter, and so this is corresponding to 10 to the 18. So simply speaking, if we have to apply 5 times 10 to the 18 per cubic centimeter doping density into 10 by 10 by 10 box, then nominally how many atoms should be placed? In this case, if we place only 5 atoms, then that is corresponding to 5 times 10 to the 18 per cubic centimeter. Oh, good. But we have no way to precisely control the number of atoms in this small box. So let's assume that there occurred a fluctuation of this number. Within this small volume, unfortunately, we have only 4 atoms. Or unfortunately, we have more than 5, 6 atoms. Then what we have is severe fluctuation of substrate density. Now it becomes 4 times 10 to the 18, 6 times 10 to the 18. Oh, since this doping density really determines the threshold voltage, this means that when we have a very small device, then now we can see the discreteness of atom count. There are 5 atoms, 6 atoms, 4 atoms that introduce severe change in our doping density, and that reflects what? The severe fluctuation of a threshold voltage. Simply speaking, as a foundry guy, we must guarantee that if you have this device, its threshold voltage is given as, for example, 0.2 volt. I guarantee. But if we follow this way, although we did our best, but internally doping density fluctuate, so some unfortunate guys shows a higher threshold voltage, and some lucky guys shows a much lower threshold voltage. There is severe fluctuation or variability of threshold voltage. That was the showstopper of our previous technology development. So people, if we just show the champion data, one transistor, it looks beautiful. However, if we build 1 billion transistor out of it, then we can find that its threshold voltage is widely spread, and designers cannot design reliably with these devices because there is a certain uncertainty. So what we have done is, okay, give up controlling the threshold voltage with this silicon part. Doping density nowadays is just kept as low values like 10 to the 16 or 10 to the 17. These numbers can be regarded as just nothing. Of course, compared with the intrinsic carrier density, 10 to the 10, 10 to the 16, 10 to the 17 is more than million times or 10 million times higher. However, from the viewpoint of doping density, that number is not significant at all. So nowadays, people think that silicon substrate is quite close to almost undoped one, and the only important factor to control this threshold voltage comes from this gate part. Then how can we change gate path. We have 6 different options for one single type, P MOSFET and N MOSFET. Then should we introduce 6 different metals? So for this guy, we use a certain metal and cover all other part, and introduce a second metal, third metal, fourth metal. That makes it really big problem. So what we do, important one is, now you understand we must control the property of this gate stack. However, this bunch of gate metal is very difficult to change. So in reality, what we are doing right now is just changing this part here, the interface between gate and this high K. Nowadays this is a high K, so that is the one we do now. Okay, so I think that now I just covered the requirement or desire to have multiple threshold voltages, and also show you that the trend. We have made a big change from substrate dominated ways to control threshold voltage to now gate stack dominant way to control threshold voltage. In these days means that within a few years, so after 2020, so nowadays it becomes more and more popular to have dipole-based multi-threshold voltage integration becomes popular. So what is it? Dipole-based multi-threshold integration means that now we have a silicon substrate, and here we have an interfacial layer, very thin, extremely thin silicon dioxide, and on top of it we have a high K. Then we introduce certain dipole selectively for one place and another place and another place, and by controlling this property of a dipole, we can introduce many different threshold voltages. Then actually how can you make it? I have no idea about the detail, but point is dipole based one does not consume thickness. So we will revisit this topic once again later, but let me just explain a little bit. So right now we are talking about FinFET. So if we just visualize its cross section, it looks like this. So of course here we have a STI and STI, but this one is electrically not active. So if we have this shape, then this height is currently we are assuming 32 nanometer, but it is much higher in our advanced FinFET node. And this thickness is currently we are assuming 7 nanometer, but eventually it is going down about 5 nanometer. That is the situation. And now we have here extremely thin interfacial layer, and also quite thin high K. After that, if we have to something on it, then we are actually free to do that, because where can you find your next fin? How much these fins are separated? You can easily understand, yes, there is somewhere there, and this distance in current implementation about 20 nanometer, and even when you go to even further scaled technology, this distance is not that much scaled. Actually, this 20 nanometer in our AP7 PDK is somewhat much scaled than in reality. So we have a sufficient difference. I mean that in the case of our FinFET technology, we were quite lucky in this sense. If we have to introduce interfacial layer and sorry about that. So we have a next fin here, and if we have to introduce another high K layer, then now what we have to do is related with this one here and there. We must do that, but the thickness of this entire high K stack is about at most 3 nanometer or 4 nanometer. So still we have much more than 10 nanometer to do something. That was the situation in our FinFET. However, now you understand we have already migrated to the nanosheet MOSFET. So in the case of a nanosheet MOSFET, the shape of our transistor cross section is no longer look like this. There are multiple stacks of a silicon layer, and there is also another layer of a silicon layer. Each of them is corresponding to this each fin. Yes, so we had multiple fins, and now we have multiple stacks. But what is the main difference between these two technologies? Just rotating these fins, actually not. The distance between these two nanosheets are much shorter than these fins. Because why we have a shorter distance? It is simply because if we allow too large distance between these two stacks, then actually our fabrication becomes too difficult. So therefore, we have to keep this distance as short as possible. So now think about this case. Now we have a silicon in this case. Then we have to introduce interfacial layer. Yes, we have an interfacial layer, and also we have to introduce high K. Yes, we have to introduce high K and high K, and after that, in order to control our threshold voltage, we must do additional job. What is the additional job? Additional job is related with adding more layer on top of this already existing silicon interfacial layer and hafnium oxide layer. So what is the problem? Since this distance is so short, and from this top side and bottom side interfacial layer, hafnium oxide, and additional treatment, so-called work function metal is growing and growing. Eventually, there is almost no space, remaining space for introducing something. This is not the end of the story. So once after we introduce this black one, which is introduced to control threshold voltage, then eventually we have to fill this remaining part with the bulk metal that should be eventually introduced. This black one is just to control the threshold voltage. So it is not that good for its conductance. So we need the real good metal. pure metal is required. However, if we have this short distance, actually it is almost impossible for us to fill this very narrow slit with our bulk metal. Then what will happen? There is no gate at all. So it is related to the failure of your device. You cannot turn on and turn off your device effectively when you make this fault in your device. So let's come back to our original slide here, shown here. Simply speaking, when we talk about FinFET generations, usually the choice was this one, so-called the choice was introducing so-called work function metal. So the purpose of this work function metal was quite clear, just to control the threshold voltage of our devices. So it is additionally added. After that, the remaining space is filled with metal, for example, tungsten. But in these days, since the distance between two channels are so close, the work function metal, which consumes a certain volume, that is not acceptable at all. So dipole is just introduced by just one single layer, so it does not consume any volume. That's the reason why we are currently in the most advanced technologies, we are using dipole. So, but that part is especially difficult and not that clear, at least to me. So let me just, in this slide, let me just introduce what we did in our FinFET technology, not the dipole-based one. That is a somewhat old technology. However, it is quite interesting. So simply speaking, if we introduce a titanium oxide layer on top of hafnium oxide, that is the typical case. So silicon interfacial layer and hafnium oxide. After that, if we introduce titanium nitride layer, its thickness is just a few nanometer. In this case, if we measure the work function of this titanium nitride layer, then it is found that its value, I wanted to give you the concrete number. However, from experiment, depending on process conditions and composition, they show certain range. Just to understand, these are known range of titanium or nitride on hafnium oxide, and this value is not suitable for our N MOSFET, perfect for our P MOSFET. Why it is perfect for something and perfect not good for something? Because we always wanted to have a certain value of a threshold voltage. More or less, nowadays threshold voltage is given as 0.2 something. So anyway, the absolute our threshold voltage for MOSFET should be higher than 0, and not that high, not that low. So in that case, this value is not good for N MOSFET. Instead of that, N MOSFET requires number close to 4 point something EV. Something means that 1, 2, 3, 0. These are required value for our N MOSFET. So simply speaking, if we just add a titanium nitride layer on top of a hafnium oxide, then it is perfect to control P MOSFET threshold voltage. Good. But how about the N MOSFET? quite fortunately, with additional aluminum component. So if we make a certain, instead of this titanium nitride, if we introduce aluminum nitride, it shows much different behavior, work function. And instead of this full aluminum nitride, we introduce a certain composition between titanium and aluminum. So simply speaking, if we have a small number of aluminum, so this is corresponding to the ratio between aluminum nitride and titanium nitride, and if we go to this direction, almost no aluminum, and if we go to that direction, there is more aluminum, then you can find that its work function varies according to this aluminum portion. Oh, so what they are doing is usually just to introduce global titanium nitride layer globally. And if you wanted to control the threshold voltage, then add additional layer of titanium aluminum nitride. Of course, additional titanium aluminum nitride on top of this here, if we really make this way, then its threshold voltage never changes. The most important point in this structure is not this guy. This interface is important. So in order to control threshold voltage, then once introduce this titanium aluminum nitride, and we must apply certain treatment to move this aluminum into penetrate into this titanium nitride layer and eventually arrive at this interface. Then if we have more aluminum portion at the interface, then we can reduce the threshold voltage or work function of this material. So simply speaking, now we have many different composition in terms of thickness. There is a certain just titanium nitride one and different thickness of varying thickness of titanium aluminum nitride layer and different recipe for heat treatment to control it. Then how can you make 6 different one? Just to changing the number of additional cycles to add titanium aluminum layer. So that is the way we make these differences. So if we are really rigorous in our example, then we must do that job in our example. However, right now we will just cover this topic with this just a bubble lecture, and we are just going to the next step. Now we assume that here we have high K. This is corresponding to high K, this purple one, and in reality we have introduced also work function method with varying thickness. For some cases we can have just a pure titanium nitride, and if we have additional adjustment, then we can have a thicker and thicker one. So in reality we have to have it. However, in this structure generation we don't care about it, and just tungsten is filled over this entirely this structure. Simply speaking, the problem of our nanosheet is related with this one. If we introduce a very short channel device, if a gate is so short, then starting from these two side walls, two spacer side, we will have a growing high K layer, and we have no chance to fill this narrow space with tungsten. So that was the problem. So therefore we eliminate work function methods from our newest technology and introduce a dipole. But right now we will just introduce a tungsten field, and after that CMP is done once again at the level of our ILD0. So therefore this ILD0 level is quite important because that is the reference level for our many several CMP. And please note that this ILD0 level was more or less determined by height of our dummy gate and also height of our hard mask, of course minus a certain process margin and over etching depth. So this is the one we have. So in this example, my final result just shows ILD0 thickness about 145, and it is known to that this value is a little bit high. So it is the actual value was around 100 something, but I have no idea what I made. Maybe I introduced a little bit thicker hard mask thickness, but anyway, this is not very much tied to the real fabrication or real process, just to live with this slightly higher one. Okay, so now we have the end of front end of line. As a final slide, let's just have a look at this side views. So now you are looking at these two different figures, and this right one shows this is the can you see it clearly? This is corresponding to the gate, the real gate of our inverter. And here okay, so okay, so okay, this is gate. Okay, so I was just confused. This is gate shared by M MOSFET and P MOSFET. And where can you find the source and drain? It is not determined yet, but anyway, this one becomes a source drain or drain and source. This is the structure in our, this is a vertical direction, and this is a channel direction. Okay, and if we have a look at different sides, still that is vertical direction, but now this direction is our so-called Y direction. Then you can find that there are N MOSFETs and also there are P MOSFETs, 3 pins, and they are separated by certain distances, and these are corresponding to silicide, and right now it is covered by ILD0. So it is not actually connected to the external world. So that is the situation up to now. Here, if we stop here, then now we can have a tungsten field, and this tungsten field is connected to the gate. Yes, so if we add something on top of this tungsten, then we can connect, we can access to our gates. Then how can we access our source and drains? Actually, they are just buried underneath our this ILD0. So eventually we have to dig out them and to connect them to the external world. That should be performed, and that kind of job is called as this one, middle Andover line, MOL. So previously there was no specific word for this job. Previously there was only two steps, front end of a line and back end of a line, because life was easier than nowadays. However, nowadays device structure becomes too complicated, and even making this intermediate level of interconnection becomes quite important. So here in the back end of line, we have regularly placed metal lines, which whose size is much larger than this front end side features. However, in the case of this MOL, middle end of line, the feature size are still comparable with this FAIR, very nanometer scale, and we have very much interaction between these two levels. So also maybe you have heard about this keyword. I'm not quite sure you have heard about this one, backside power delivery network. This is a hot keyword in our manufacturing and technology guys, and this is also related with the middle of a line. How can we supply our ground signal, and how can you supply our VDD signal into our transistor? That is considered in our middle end of line job. Once after that, back end of line goes. So let me just summarize the FAIR steps. So FAIR, front end of line, is represent all process steps up to the completion of a transistor itself. Now we have already well fabricated transistor. It has its own gate, its source and drain channel, all are made. However, that is not connected to the external world. That is done by our MOL and back-end of line. So let me just summarize its major steps. First, we have to prepare uniform fin patterning. So after that, in this case, already fins are cut. Cut means that if we have X and Y direction in our layers, then when we draw fins, and then fins are usually drawn in this way, and also they are drawn in that way. This horizontal gap or cut line, that cut region is already made when we make a fin. However, along this Y direction, there is no cut right now. Everything is just uniformly spaced by, in our case, 27 nanometer pitch. Once we have a fin patterning, then we must fill this remaining part with STI. So this part are filled with the STI. So now fins are isolated. After that, dummy gates are patterned. So dummy gates means that now we have another uniform line. Another uniform lines are running. After that, we introduce spacer nearby here and here, because these spacers are introduced to separate source and drain and gates. Without this one, they can be just shorted. Then now we have a small difference, or small here, small space between these two spacers, and inside this guy we introduce source drain epi. Now we have diamonds here and also diamonds here, and on top of this diamond we perform salicide. Yes, so that is done for our source and drain. After that, this dummy gate, which is polysilicon, that is removed, and also we introduce high K stack. High K stack means that growth of interfacial layer, high K stack, also certain work function metal. After that, gate is filled with typically tungsten. That is the one we have done up to now in this course. Of course, we have to go to the next level, middle end of line, but so let me just make a pause here and let's go to our homework number 15. So up to now we have done quite much jobs for mimicking the ASAP7 PDK. So please try to follow it and give me your report on this entire failed process. Then now I have to give you some hints about your term project. So we have no midterm examination, and we don't have the final examination. The only thing you have to do is simply this term project. So your term project should be made as in a form of a video clip, and then submit it to me. Then based on the quality of your video submission, your final grade will be determined. And although this is not the exactly matched to our course, I strongly recommend you to watch the term project videos submitted by our previous students for TCAD 2022 lecture. It is not for our Ångström-Craft code. Actually, Ångström-Craft code initiated just a few months ago. But anyway, the structure, I mean that the lecture structure is quite similar. They perform some numerical exercise on their own interest. I guess that these are the structures they have made. This is not. This is just a lecture material, and you can find that there are so many different structures. I strongly believe that all of you have your own different interest on semiconductor devices. To some of you, you have some interest, strong interest on memory devices, or some of you are really wanted to study more about FinFET. Some of you wanted to apply it to the, for example, nanosheet MOSFET or complementary FETs. So it is allowed you to do what you wanted to do. So because you have Ångström-Craft which can generate just to mimic the process procedure, so please do not restrict your interest to the one we have studied up to now. I will be very happy if you select a very uncommon one or not covered in this lecture course. So anyway, please watch the term project, then that will give you how much you can do with these tools. I think that you have more tools, so I believe that the quality of your project can be even higher than those provided by students in 3 years ago. They just work with one single program which will be introduced from now on, and now you have a combination of a processor emulator and these two. so you have more chances. So please think about this one. Now you have just about 1 month before submission of your term project submission. So now it's a time to really start your term project, at least in initial idealization. Okay, so this slide is taken from our lecture 3. My original plan was to introduce these tools and make a combination of use of these tools, but unfortunately, or in some sense fortunately, we have spent quite a lot of time only on Ångström-Craft up to now. We have made a really detailed discussion about up to now fair procedure of FinFET representative FinFET technology, and we have used it so far, and not yet done. We must do middle end of line emulation. Also, we have to do the back end of line emulation. So, of course, I'm not saying that we can go to metal 10 or something, but anyway, we can go to the first a few metal lines from this kind of job. That is remaining, but I think that we are already lecture 15, and guess that we have more next countable number of lectures remaining. So if we stop here, then entire semester will be consumed with only this program. So it's not that good, especially from the viewpoint of your term project. You need a little bit more. So that's the reason why I make a pause of use of Ångström-Craft, and now we will start simple discussion about device simulator. What is the difference between these two tools? They have different purposes. Up to now, we wanted to make the structure. We wanted to make the geometry of our transistor. Then, is it good in its current conduction or not? That cannot be answered by this Ångström-Craft code, because this is specialized for structure generation. So now we will introduce our second code, G-device, and this one is specialized to predict and calculate the electrical performance of a given structure. Simply speaking, if you change your process emulation, then you will have a slightly different device structure. Then with slightly different device structure, you will have slightly different electrical performance. If you like it, then you can keep this way. But if your performance is not improved at all or degraded, then actually you have to come back to this step and change your parameters again and again, repeatedly, till the satisfying the performance. So this is the usual way we do, and today we will talk about how can we use this G device code. So maybe you can ask me, okay, G device is for device simulation, electrical property. So let's just dive into the electrical property. But we need structure, device structure. So then you can ask me this question. Up to now, we have almost devoted our entire semester to structure generation. So why don't you just use the structure generated up to now? Then now let's start the calculation. But unfortunately, we have some missing feature in this structure generated by Ångström-Craft. Here, we have nothing about doping profile. Do you have a source strain doping density in your structure? And where can you find your contact? Where is your gate? And where is the source and drain? Of course, we have not finished our MOL structure, so it is quite natural to have no contact. But even after that is done, but we have not covered the capability to make this contact and doping. So I wanted to give you a quick way to introduce doping and contact in our G device itself. Although this code is not specialized for structure generation, but anyway, for simple structure, it can generate its own structure. So today I will introduce it that way. First of all, you have to check again whether you can access to this code. That was actually homework number 3, and all of you guys successfully did homework 3, so I'm certain that you can obtain this result again. So when you type just G device and it says that it's a name and version number and something, and of course it will have some complaint. What is the complaint? We need to specify the info file name. Then what is the info file name? We have to fill that file. So let's make a simple example file. Okay, so we have a system. So this is the entire input file. You can just type in your text editor and save a certain name, any name you wanted to do, and let's say that this is called as AAA.cmd. Then if it is saved as AAA.cmd, then just type G device AAA.cmd, then enter, then you will have the execution of this one. Let me just explain what is it inside this file. Please note that although these two tools, OngstromCraft and GDevice, are written by myself, however, they do not share their grammars. So they are completely separated program. So the previous commands for OngstromCraft never works. So you have to learn its own grammar. And here you have something called as thing, and please do not change anything. So if you change anything, then you will have some problems. And this one just shows that there is a certain object called as structure, and its type is mapmaker type, and this mapmaker is a nickname of a structure generator. So it's not like OngstromCraft. OngstromCraft is entirely built for structure generation, and this is just a simple drawing tool to generate a simple structure. So light version of mapmaker. And now here you have a second line, and here type 3D means that we will make a 3D structure. Of course, if you say 2D, then actually you can even make a 2D structure, but I will not talk about 2D generation, and this becomes 3D, and CGNS equal to pn.cgns. So simply speaking, if you say, instead of this pn.cgns, if you type AAA.cgns, then you will have a structure named as AAA.cgns. So you can change it, this one. And the remaining parts are quite clear. Inside it, we have a cuboid. Cuboid just to describe the size of our entire system. Please have a look at this triplet, x0, y0, and z0. It specifies a position in three-dimensional structure. So this is corresponding on origin point. And another one is x1, y1, z1 is another point which is diagonal in this cuboid. here you can see that this one is 1 micrometer, 1 micrometer, and I guess that this is 2, means that 2 micrometer. There is difference in the unit. In the Ångström craft, the numbers you type was in nanometer scale, and now in this case everything is just meter scale. So simply speaking, if you wanted to make 1 nanometer, and you have to type 1 e minus 9, this is corresponding to our G device specification. But anyway, now we have 1 micrometer, 1 micrometer, and 2 micrometer size cuboid, and when we visualize it, actually it becomes a tall box. So here we have 1 micro and 1 micrometer, and this is corresponding to 2 micrometer. You just say that there is a cuboid, a tall cuboid that is specified this way up to now, and now you have another one, nx, ny, nz. This is required. These are required to divide these x direction, y direction, and g direction. What is it? We will introduce two intervals for this 2 points. Sorry. So this means that we will introduce 2 points for this 1 micro long size. Simply speaking, we will have 2 points along x direction. Also, ny equal to 2 means that we will introduce 2 points along y direction. So by doing so, we do not introduce many points. So let me just ask you this question. If I say ny equal to 3, then what will happen? If we say ny equal to 3, then we will have 3 points for this y direction. So we will introduce additional 1 point for our y directional coordinate. If we say 100, then we will have more and more points. And you can find that example here. nz equal to 201. So since this is 2 micrometer, it means that we have 10 nanometer spacing for neighboring points. So we have 1 point and 10, 20, 30, 40, and repeatedly up to 2 micrometer. We will have quite a dense grid along g direction and along x and y direction. We have a much relaxed one, because actually this structure is really one-dimensional, and we have no variation along x direction and y direction. Other ones are just written here, and now you can name its region. So please don't be confused with same name commented, region commented in Ångström. They are not compatible. They are completely different, and you can specify name and select material. You cannot say arbitrarily. If you say silico without n, then there is no material like this. So there is a silicon. Already their names are predefined, so please do not make any adventure to change your material. So silicon is a given one, so you can select it. And also you can find here the numbers starting from I. This I means that these are integer in this grammar. So you must specify the index of your point. So please have a look at this one. ix0, iy0, ig0 means that the index of your 1 point. This is corresponding to this one. And another one is ix1, y1, iz1 is corresponding to this midpoint of your structure. So simply speaking, this region specification means that half of its lower part is named as p-type region, and it has silicon material. You can repeat the same thing with upper part, and upper part means that n-type, that is named in this way. So let me give you one simple example. Instead of this one, I just made a little change. 180 and 180. Then what will happen to this structure? If we introduce this change, then our bottom p-type becomes much taller. So the boundary between these two regions, n-type and p-type, will found here about 1.8 micrometer position in its g coordinate. Okay, so since time is up, I will just stop here, just to leave this example to you. So please just cover the remaining lecture material. I will not repeat this one. So my suggestion is just type the given example file and execute it. Then you will have a CGNS file, and with help of this already uploaded video, how to draw a cut line graph, please try to visualize your structure. I think that some of you coming from the graduate school can do it quite easily, but if you are coming from undergraduate level, then maybe this is the first time you see this kind of things. So please spend your time to get familiar with this one. Okay, thank you, and see you next Monday.